Okay, everyone. So we're back. We are going to be studying maximum likelihood and least squares. Now, this section, the next few sections are actually very, very important. They're important first in their own right because this kind of problem, the kind of problems we're going to discuss, applying maximum likelihood in a supervised regression setting, that can come up a lot, and so it's useful to see how to solve it. And you will see it's kind of a simple machinery for carrying that out. But also we're going to be studying it under very simple probability models, which allow us to really understand what the geometry of the situation. And so instead of just running through the mechanism and just getting an answer out and hoping that it's right, in the case we're going to consider here, we can actually really understand more deeply what the actual geometric significance of what we're doing is. And that gives us insight into this problem, but then that insight you can try to then carry to more complicated settings. So it becomes a very good also exercise of trying to turn your geometric knowledge into linear algebra and vice versa. So working with that in kind of a very tractable setting. Now the way I'm going to cover it, I actually tried doing the next few sections all together, but I think I wasn't able to do it justice. So what I'm going to do is in this particular session, I'm going to cover just this 3.1.1, which is just setting up the problem and then going through the machinery for how to get an answer. And we'll see how that's done, and then we'll kind of come across some equations which at the beginning might not have any real meaning to you. It's just something that pops out. And so for this particular session, I'm just going to ask you to kind of to bear with me. We'll get this like design matrix, like where is that coming from? What does it mean? Now the meaning of all that stuff is going to become clear in this next section, which is the geometry of least squares. So that's what I'm going to cover in the next video. And I'm going to, he's given one paragraph to it. I'm going to actually cover it in some more depth with more pictures, hopefully. I mean, this is the key picture you need to think about. But we'll go into it, try to really understand what's going on, and then we'll revisit these equations when we've done that, and to really understand kind of what's going on and what this all means. So in this first pass through, just bear with me and just learn to use the machinery, kind of the gradient, setting gradients to zero basically. That's all we're going to be doing, and we're going to get answers out. Also, I think the next section that comes is sequential learning. In some sense, it's actually very connected to the one we're going to do right now. Just how to turn, our gradient descent into kind of a sequential gradient descent. So I will cover that in this current section as well. So what we're going to cover is, in this section today, sorry about all the scrolling, is going to be this plus 3.1.3. So that's what we're going to talk about. Okay, so let's get to it. So what is he saying? So okay, in chapter 1, we fitted polynomial functions to data sets by minimizing a sum of squares error function. So go back to that video if you've forgotten. We also showed that this error function can be motivated as the maximum likelihood solution under an assumed Gaussian noise model, and this was really cool, right? So we came up with this like heuristic idea, like this energy idea looks useful, seems reasonable, but then it turns out that it has a probabilistic interpretation. That's really powerful because then it allows you to understand A, whether that interpretation kind of applies to your setting, even approximately, and B, how to extend it. So things become suddenly much less ad hoc. Now it says, let us return to this discussion and consider the least squares approach and its relations to maximum likelihood in more detail. Okay. And so I think this is going to be, it's going to be important because maximum likelihood is not it's just a general approach. It doesn't have to actually be tied to least squares. Least squares comes up when you're actually using a Gaussian noise model, because the Gaussian likelihood introduces a sum of squares terms that you try to minimize. So these two things are actually quite separate. So it's good to keep in mind. But when we have them together, then we get some very tractable answers and some easy answers that are A, easy to compute, and B, for which we can get some geometric understanding, which we'll talk about in the next session. Okay, so again, now we're in the supervised setting. So we have a target variable, and it's given by a deterministic function y of x, which is your data, and w, which is your weights that you're trying to learn, with additive noise. So that t is this deterministic thing plus this Gaussian noise term. So epsilon is zero mean Gaussian random variable with precision, inverse variance, equal to beta. So therefore, this probability that we have, we can write it as the probability of t is the mean value is the deterministic bit because our epsilon has mean 0, and then the only source of variance is that noise term, which is contributing 1 over beta, which is the precision. So this is, and right now we haven't said anything about what y of xw is going to be, but we're going to do so shortly. Okay, now, so just recall that if we assumed a squared loss function, then the optimal prediction for a new value of x will be given by the conditional mean of the target variable. Okay, so one thing that's important to point out here, this squared loss thing is different, is unrelated to the least squares. So this is kind of something you're going to add on. So the question, as we discussed in decision theory, is you've got this probability distribution on your on t, and now you're like, well, what value of t do you report? And so we saw that depends on how you penalize being wrong. So in the case where let's have a loss function, let's say the loss of true value versus the one that you report is, if you use a squared loss, which is completely separate from, this least squares thing, it's just the loss function, then the optimal prediction is to take, given this probability distribution, the optimal summary of it that minimizes this loss is to give the conditional mean. So in the case of a Gaussian conditional distribution in the form 3.8, the conditional mean will simply be, so this is just the conditional mean for whatever p, not just the Gaussian one. But for our Gaussian case that we have here, where the conditional mean is just the mean, right? So once you're given x and w, the mean is determined, that's what you report. So note that the Gaussian noise assumption implies that the conditional distribution of t given x is unimodal, so mean handling one peak, which may be inappropriate for some applications. And we're going to see how to extend that way in chapter 14. But for now, we're just going to live with this Gaussian thing. Okay, so that was a situation for with one data point. And now I said, now consider a data set of inputs with corresponding targets t1 to t of n. And so remember, the game is always, yes, we know what the values are for those x's. We want to come up with a w that allows us to predict new ones based on this data. So we group the target variables into a column vector that we denote by t, where the typeface is chosen to distinguish it from a single observation of a multivariate target, which would be denoted this other font t. Okay, making the assumption that these data points are drawn independently from the distribution 3.8. That was this one. And this independence assumption is the crucial one. I think through most of the book, I imagine this is going to be, because that's what lets us simplify our life, basically. We obtain the following expression for the likelihood function, which is a function of the adjustable parameters w and b. Okay, so what's happened here, and you should be getting used to this by now, the first step is we've said because of the independence, this probability is a product of the probabilities of each data point. So now it's going to be p of tn given. And notice that now we've changed the form. So he says we've now plugged in a particular form. But that doesn't matter for this independence assumption. We could have just put y in there. So we've got this product from independence, and now we actually kind of fill in what it looks like, what these probabilities look like, and it looks like this. Okay, so product of Gaussians. Note that in supervised learning problems, such as regression and classification, so when the targets are discrete, we are not seeking to model the distribution of the input variables. So we're not necessarily carrying on like what's the probability of x given the targets. We just care about what's the probability of the targets given the inputs. Thus x will always appear in the set of conditioning variables. So we're always going to have like an x sitting on the left side. So we will now drop the explicit x from expressions such as this in order to keep the notation uncluttered. So just remember down here, for example, there should be an x, but he's going to drop it because it's just going to be less, it'll be tidier that way. Okay, taking the logarithm of the likelihood function, again, because if we want to maximize something, we can equivalently maximize this logarithm. and it makes the math much easier. And making use of the standard form 1.46 for the univariate Gaussian, we have, so remember, this one you should have memorized by now. And so Gaussian is going to be 1 over root 2 pi sigma squared of times the exponential of 1 over 2 sigma squared of, whatever your data point is minus the mean squared. But now we've got variance, we've got precision, so let's zoom in here. So, oops. So let's get rid of that. So now that's just going to be replaced by a root beta up there, and beta there. Okay, so that was for the Gaussian, of course. And now we're going to take the logarithm. So we're going to get a bunch of logarithm. What's that going to do? Well, it's going to take the log of this thing for each data point. So now we're going to get a bunch of terms popping out. So this root b term, when you take the log, it's going to become 1/2 ln of b. And there's n of them, one for each data point. So that's where this comes from. Similar thing happens with the 2 pi. The interesting bit is what happens with the terms that are inside this exponential. And so what they look like is going to have this scaling of b, of beta, but then it's going to be this kind of this is where the sum of squares comes from. So this was kind of sitting inside of, there's going to be an exponent of, there's a beta there as well, minus, beta times this. So that was, this was like the, this was a normal distribution at each point, right? They were giving the target where the observation was t of n, and the mean that we were predicting was this function, this weighted sum of these features. So that's where we're getting this sum of squares. And so now our job is two things. We're going to want to figure out what beta is, the precision, and we're going to figure out what the weights are. And for the first part, we're going to figure out what the weights are. So let's do that. Okay, so having written down the likelihood function, we can use maximum likelihood to determine W and beta. Consider first the maximization with respect to W. As observed already, we see that the maximization of the likelihood function under a conditional Gaussian noise distribution for a linear model is equivalent to minimizing a sum of squares error function by. Okay, so I don't think you don't need it to be a linear model. So remember, the linear model aspect was that it was linear in the parameters we cared about. And so because the features could be whatever they were, and that gives us the flexibility, the power of linear models, that you can have kind of nonlinear features as long as you're looking at a linear sum of them. So this is the linearity we care about is W. So the only thing I was kind of a little bit questioning was that the likelihood of a function under a conditional Gaussian noise distribution for a linear model is equivalent to minimizing a sum of squares error function given by ED of W. So that's true. Yeah, I guess I was going to say it doesn't need to be a linear model. It could be anything. It'll still have a sum of squares. It'll just be the dependence on W could be more complicated. But certainly for a linear model, that's what we're going to get. So let's highlight this. That is equivalent to minimizing a sum of squares error function given by that. Okay, simples. So now all we're going to do is set the gradient, compute the gradient, and set it to 0. So that's all we're going to do. So let's do that. So this is kind of a good time to go and recall how to take. We're taking a derivative of a scalar function with respect to a vector variable. You can do it in single elements as well. So you can compute, d of e with respect to wi, and you'll get the same answer. But it's really good to get into the habit of it'll just save you so much more time if you can actually remember how to do the full derivative with respect to the vector. So just make sure you're comfortable with that and get more. You'll get practice through stuff like this. So this is just really good exercise to go through and make sure that you take the derivatives the way you think, and you're getting the same answers that we're going to be finding. Okay, so we'll just take the derivative ourselves here. So the gradient of this whole logarithm with respect to W. Notice that the weights don't show up here. They don't show up here. It's only this term that we care about. Okay, So the gradient of log likelihood takes the form of, so let's take the gradient of this thing. So it's going to be the gradient of minus b e d w, and the constant terms aren't going to really matter because we're going to end up setting this to 0 anyway. So what does it look like? Well, this is going to equal to sum on n equals 1 to n, so there's a 1/2. But now this term is just it's a scalar, so it's just going to be 2 times tn minus w phi xn, and then so it's chain rule, and now we're going to take the derivative of the linear operation on the features with respect to w, and that's just going to give us phi of xn transpose. So this cancels that, and that is where we get this equation. Yeah, one thing, and yeah, so those, I'm just making sure before I tell you the thing I'm going to tell you, I just want for what I'm about to tell you, it's important actually which direction, what the signs are, because it won't be just about setting it to 0. So there's a minus beta there, and there's a minus, so that minus is going to cancel, and this is indeed going to be the gradient. Okay, so what I was going to tell you was that this already has an interesting interpretation, because what it's telling you is, so it's telling you this is the gradient with respect to w. So imagine you have these weights, and you want to move, adjust them. Now it's telling you that the way you should adjust, so each data point is going to give you an adjustment of the weights in the direction of this feature map, this feature computed on that data point. Remember, so phi of xn is going to be equal to, and these are scalar functions, these are just single values. So the first feature on xn, the second feature on xn, all the way to, I think it's like m minus 1. Right? So this is kind of a vector, it should be transposed. And what it's telling you is that the weights are going to be adjusted, pushed towards the value of the features on a data point. And how much are they going to be pushed towards it? I'm going to erase this stuff just so it's easier for us to see. So how much are they going to be pushed? Well, there's going to be pushed towards it by this difference. So if the projection of, if the overlap of the current weight vector projected onto this feature, there's kind of, you can think of this as kind of like as a gain. It says if this kind of overlap is quite small, well then increase the weights in the direction to make that overlap a bit larger. So essentially, when do you stop adjusting the weights in this direction? It's when t of n equals, when this term is 0, when the target equals the projection of the weights of the features onto the weights that you have. Otherwise, you keep you try to increase the weights so that this quantity increases, that the output that's kind of being contributed by this feature increases. So I don't know if that was maybe that wasn't super useful, but I just want to kind of give you a sense that you can think of this as kind of what it is doing is kind of adjusting weights, and we'll see that in the stochastic case. You're kind of adjusting the weights in a particular direction. That direction is in the direction of the features on that data point, and the gain has to do with the difference between the target and how well these features capture the target. So yeah, just a little side note. Okay, so anyway, what do we do? So now we set this gradient to 0. So, and it's easy to see that it's going to be what? So it's going to be the sum on n equals 1 to n of t of n xn transpose. And then we're going to have another sum. So it's going to be a sum on n equals 1 to n weights phi of xn, phi of xn transpose. Right? And so now we can take this on the outside, and now we get this expression. Now we're going to set it to 0, so I'm going to transpose everything so that we don't have to deal with weight, the weight transpose, but with the weight itself. So this whole thing is equal to also sum on n equals 1 to n, tn phi I'm going to say it's not equal because we're transposing, but it also implies minus the transpose of this term is itself. It's because it's symmetric. And then there's going to be a weight on the outside. And so then if we set that to 0, so equals 0 goes to the sum on phi t times w is equal to this sum on n equals 1 to n of phi times t, phi xn times t of n. Okay, and then what we're going to do in the kind of the very last step is now we're going to pack these into a particular matrix. So these are kind of the features being computed, these feature vectors, but now we're going to pack them into a particular matrix, which is going to be called the design matrix. I didn't know that name. I just know what that matrix is. So, okay, guys. So I thought that I actually needed more room to explain what was happening here. So I've erased everything. I'm going to show you exactly kind of how we get to these equations. So there's no mystery, but it's useful to work through it. So remember where we were was we had this particular this equation. We took the transpose and it gave us this, right? So a sum of phi times t of n, and then phi times phi transpose times w. And now we want to kind of somehow massage this to end up with something like this equation down here. How do we do that? And it's kind of a nice thing to go through. So let's go. I made a new page where we can talk about this. So if you just arrange things around, you get this equation, right? Because everything equals 0. So we rearrange things and we get this equation. And now we want to see whether we can massage this into a matrix and vector equation, just to give us a better sense of what's going on. So the first thing to do is let's start with the right-hand side. It looks like the simplest thing. And we see that we can actually write this as phi of x1 to phi of x2, so all the way to phi of xn. So we're gonna pack this into a matrix where the columns are the features evaluated on each data point. Oops, let me just actually map this out fully. So here times t1 to tn. So this is the same as, so we're going to now define this thing. This is going to be our big vector. We're going to call this phi, and this is our vector t. So this is a matrix times a vector. So that's great. So that we simplified the right side. Now what about the left? Okay, so this one looks at first might be a little bit tricky, but the thing to remember is this is really useful way of multiplying matrices, right? So remember that if you're multiplying two matrices, so you can actually do it by taking, this is the same as, k equals 1 to however many you need, to have, let's call this the number of columns of A, the number of rows, we'll just call it k. It's equal to the sum of the kind of the product, the kind of outer product of the columns of k times the rows of B. That's a very useful thing to know. And so it looks like we actually have a very similar thing happening here, right? We have an outer product of columns and rows. So we can actually write that as the product of two matrices where one has columns phi and the other one has rows phi. But the one with columns phi is already this guy, and well, the one that has rows phi, well, it's this guy transposed. So you can just write this as phi transpose of W. Okay, so that's how, so we'll just bring that down here, and we get this equation. Okay, so now just to kind of connect to what he's doing, look at our phi matrix. What does it look like? Our in detail. So it's going to be, phi 0 times x1 all the way to phi m minus 1 x1 to phi 0 xn all the way to phi m minus 1 xn. Now, for whatever reason, it might become clear later, but he actually chooses to define the matrix the other way. So we'll call, phi, bishop is actually the transpose of phi, the phi that we have. So his one is going to actually look like, he is going to have the feature vectors, the features apply to each data point along the row. So it's going to be, notice how we're going from phi 0 to phi m minus 1 on one data point along the column, so we're going to do it along the rows. So it's going to be x1 all the way to phi of m minus 1 x1, and then again it's phi, so it's always the same. Now it's kind of the single features are along the columns evaluated on each data point. And I think it's going to be used, this is going to be actually more useful when we talk about the geometric case. So I think that's why he does it that way. So we'll see why it's actually more useful to work with his transpose than what we have. But ours was just a way of getting things into it. They're equivalent, so it's just whichever one you prefer. And it's going to be phi of m minus 1 x of n. Okay, so in terms of the phi of bishop, it's going to be, our equation is going to look like, so phi transpose is, so this implies that phi equals phi bishop transpose. So we just plug in that phi bishop phi bishop transpose phi bishop times weights equals phi bishop transpose times t. Okay, so that is the equation we end up with, which he calls, yeah. So that's basically, that's exactly, so the previous step to this, and obviously we're going to work with his now. Phi of t times t, and now you just take the inverse, apply the inverse of phi minus 1 to both sides to solve for w. And now, so the interesting thing here is that if you look at this, so if you look at kind of our initial equation, right, we had a setting where we were now looking at, t is equal to, we're comparing in the vectors. I won't get into that. We'll get into that when we look at the geometric picture. Okay. Either way, so now we ended up with this equation. We applied the phi t phi minus 1 to both sides, and now we came up with this solution. So we call this the normal equations for least squares problem, just a name. And here phi is an n by n matrix called the design matrix. So notice for him, his each column is going to be one of the features. That's going to be kind of a handier way of working with things when we look in when we're looking at the in the geometric case, I believe. But we'll see when we get there. The quantity, so this quantity here is the pseudo inverse of the matrix phi. It can be regarded as a generalization of the notion of matrix inverse. Okay, so this actually has really cool properties. We'll talk about in the geometric session. The reason why he's talking about inverses is like why does he suddenly talk about this? It's, look, if you're trying to find some setting of the weights that's approximately equal to t. Well, if phi was square, you could just apply the inverse of phi to both sides and get w is equal to phi minus 1 of t. But the problem we have is that our phi in this case is actually tall, right? So the question is, how, even without getting into the geometry of it, how do we define the inverse? And so we essentially want to do something as close to the inverse as possible. And it turns out that there is this concept of the pseudo inverse that kind of gives us something close, and it's going to be close in the sense that, look, you're not going to be able to. So what is the, and we'll talk about this again, but what does the inverse do, right? It gives you, when you can invert it, it gives you a w where when you multiply w by phi, you get t exactly. Well, in the situation we're in, we can't actually, usually in most cases, we can't actually match t exactly, but what we want to do is we want to get as close as possible in the least squares sense. And this pseudo inverse, the property that it has is that it gives you that value. So it doesn't, you won't be able to match, phi w won't equal to t, but it'll be as close as you can get within the limitations of this kind of tall matrix. And we'll talk about all of that in the next session. But anyway, that's kind of a hint of where this inverse stuff comes from. Okay, and then finally he says, at this point we gain some insight into the role of the bias parameter. So he says if we make the bias parameter explicit, then the error function becomes, so now we're pulling out the bias parameter. So now there's w naught, and then j is now going from 1 to m minus 1. And if you set the derivative to 0, so you guys should do this, you get that the bias is the difference between the mean of the targets and the weighted sum of the means of the features. So where we have defined so the bias compensates for the difference between the averages over the training set of the target values and the weighted sum of the average of the bias function. So I guess what he's trying to say there is that yeah, if there's kind of some offset that your features are going to induce, this bias allows you kind of essentially get rid of it, this w naught term. Okay, and the next thing is, we're going to maximize the log likelihood function with respect to the noise precision parameter. And so if you go up to the top and you do this, just take the derivative, you see beta shows up there and there, you end up very quickly with this expression. And he says that it's got this cool property that's that it equals the residual, that the inverse of the noise precision is given by the residual variance of the target values around the regression function. So all that means is, you're going to have this whole procedure is going to, you're for, let's say your data point, let's do it in kind of a one-dimensional case where you've got, x1, let's say xn, and your targets are, I don't know, like something like that. Actually, your targets won't be like that. They'll be, they will look like, and now you will fit a curve through them. And so now the error that you get at each point, when you add up the kind of the variance, so so if you then, I don't know what's the best way of explaining this. So now if you subtract the targets, so you can look at every point at each one of your data points, you can plot now this residual at each data point, which is going to be, t of n minus, well, now that's just going to be this mean zero thing, because your function will have, your fit by design will have made sure the mean of the residuals is 0, and you'll just kind of get a little bit of noise, right? So there'll just be a little bit of noise around your fit. So you're kind of capturing this variance. So the mean is going to have, your prediction will have kind of gone through, your prediction will kind of be the mean at each data point, and then the variance that's left over will be captured by your precision, basically by 1 over your precision. So we see that the inverse of the noise precision is given by the residual variance of the target values around the regression function. So, and that's kind of, yeah, let's highlight that. And that's kind of like, that's, congruent, that's reflecting our model of the data, right? Our model was like the data is equal to, we had our probability of data given xw was that it's kind of normally distributed with some, xw, and then some precision. So now essentially we go through every data point, we subtract this mean value, and then we see, well, how much noise is there, and we add up the average variance of that noise, and we say, well, that's going to be our variance. So that's kind of how it works. Okay, so I think that was that, and now we're going to skip this section for now and go to the sequential learning. So how to do this? We did this all in batch, right? We had the entire data set. So now let's try doing this. Can we do this kind of on the fly? It says batch techniques such as maximum likelihood, which involve processing the entire training set in one go, can be computationally costly. We already talked about this for large data sets. As we discussed in Chapter 1, if the data set is sufficiently large, it may be worthwhile to use sequential algorithms, also known as online algorithms. We talked about this in the last chapter as well, in which the data points are considered one at a time and the model parameters updated after each presentation. And then, again, sequential learning is important for real-time applications in which data observations are arriving in a continuous stream and predictions must be made before all the data points are seen. So lots of really good reasons why you want to do this. And so now you're just going to basically do the kind of the obvious thing here, which is, so I guess it's called, by applying technique of stochastic gradient descent, which is really important and people use it all the time now, also known as sequential gradient descent. So he says, look, if you got your error function comprising a sum over data points E, is probably what you would think of doing as well. A sum of a contribution from each data point. Then after the presentation of pattern N, the stochastic gradient descent algorithm updates the parameters of W using take the weight and then add minus eta with respect to the gradient. So I guess one way you could think about that is you can say, well, if E is equal to sum on E of N, then the gradient of E is going to equal to the sum of the gradient of E of N, so the gradient of W. Now in the batch setting, you would kind of compute all of those gradients all at once and add them all up. Well, you could say, well, okay, in the online setting, what if I just did that one at a time? And that's essentially how you end up at this point. So instead of like in the batch setting computing the gradients for all the data points and adding them up, you just do them one at a time, and you update your weights one at a time according to the gradient of the current data point, and you essentially end up at this algorithm here. So there's going to be some learning rate, and it's important to set the learning rate properly. Remember, we talked about the Robbins-Monroe algorithm, which kind of boiled down in that case to just having a good schedule for how to set these weights, this learning rate. So it's important to do that properly, but if you do it, you can converge to the solution. We shall discuss the choice of value for eta shortly. The value of W is initialized to some starting vector W naught. And for the case of the sum of squares error function, this gives, so we just plug in the gradient. And notice that we're going to use the weights that current value of the weights to compute the fit to the newest data point, multiplied by learning rate, and continue. So this is known as least mean squares, or the LMS algorithm. So I think just kind of a really intuitive thing. You would probably think of it yourselves if you were in this situation. Okay, cool. So I think that's all I want to talk about. So next time we'll spend a good chunk of time discussing the geometry of least squares. Really important topic, really good practice for linear algebra, geometry, and also giving you intuition for what's going on when we're doing these fits. So you can extend that to more complicated settings. So hopefully you found that useful, and that let me know if you did or if you didn't, or any comments. I always appreciate them. And I will see you next time, hopefully, when we'll discuss the geometry of least squares. So bye for now.